Kia ora koutou. I'd like to thank the organisers of the Architecture Science Association conference for this year for inviting me to give this presentation. It's given me the opportunity to reflect on 40 years as a physicist conducting research in a School of Architecture. I've entitled it People and Buildings because it seems to me to be the thread that links the nearly 40 years of my career. I'm sure this video was an attempt by TV3 to collect a news bulletin filler with an entertaining clip of people's jackets and skirts being blown about by the wind. But they captured something else altogether. What you saw was predicted by the wind tunnel test done for the developer on this building and submitted to the City Council as part of the planning process. We have wind regulations in Wellington designed to signal these issues. If the wind tunnel test shows that a building may cause a significant problem, then the building is normally greatly modified. This building was eventually given resource consent after submission of a third opinion. The wind tunnel test and the Wellington City Wind Advisor agreed design changes were necessary. The opinion states almost any building of substance constructed on the site is likely to have a similar effect, which is what the wind tunnel test showed. Less substance was needed. I understand the developer's desire to overrule the initial environmental impact assessment. Their rule of thumb estimate of the value of the site, I presume, will have been based on the height limit for the area and the site area. Multiply the two together, you get the volume you can build. However, the video illustrates the problem of application of such a simplistic rule of thumb. The height limit is a crude urban design tool intended to reduce adverse effects on the local environment, such as wind, shade, the amount of water and other resources that are needed to be supplied by the city. Unfortunately, following that crude rule of thumb and not the detailed wind analysis leaves us a problem that is likely to last for at least the next 50 years. This video is of Midland Park in Wellington in May 2007. You can see the people in this video mostly choosing to sit in the sun, as it was cool. They're plotting the sun's movement across the site by where they sit. Another paper in this conference, presented by Kasun Pereira, a PhD student of mine, has taken this 2007 study and extended it. He is demonstrating that conventional physiology-based indices of external comfort that combine the obvious measures of wind, sun, and temperature are unreliable indicators of people's preferences in the real world. These indices of comfort appear sophisticated, but they're little better again than rules of thumb because they ignore people's preferences and behavior. The issue of performance indices, what people want, and rules of thumb also arises when we look at light. These early images on the left are of the Museum of Modern Art in San Francisco. Only the last picture, the one with the trees in it, is of reality. The other two are renders. Clearly, we've been able to model light like this accurately and represent what a building could look like accurately for at least 30 years. Instead, we have very crude measures of code compliance and very crude measures for use in design, so people suffer in their apartments. Crystal Stewart's work 12 years ago at the School of Architecture measured daylight in apartments and demonstrated that 50% of them didn't comply with the minimal 30 lux on the floor at the rear of the living spaces as required by the building code. We can do better. No one has asked, is this what apartment dwellers want? Crystal used climate-based daylight modeling to develop a simple compliance tool, which would use a few simple site-relevant measures to identify the risk of non-compliance with the building code. We show it here on the right. Enter these values and it will tell you yes or no. That more detailed study is needed. We've had her risk checking tool available online at Reaches Technology for the past 2.5 years. Plan is not to avoid detailed analysis, but to ensure it's only done when needed. I do need to point out that guides as to how to do climate-based daylight modeling at the moment typically focus on office daylight, illumination on a desktop, not illumination of a room or a living room or a bedroom. Haman, another of our PhD students, is currently seeking the opinions of house buyers on what environmental qualities, including light, they want in a dwelling, necessary to improve codes and standards. Over the years, we've also looked at classroom acoustics. Ackley, a current PhD student, has been looking at the broad issues of indoor environmental quality in school classrooms. In his work, we've noticed that while there are minimum standards for temperature and light, in acoustics there's only a maximum. It is for the background noise. As the earlier work of Sarah Leggett, a Masters of Building Science graduate, has shown, understanding noise in classrooms is not a simple rule of thumb issue. She looked at 10 case study classrooms with this number of students and this number of teachers, some of them open plan, some of them single cell, a couple of them with soft carpet, that is underlay under the carpet, the rest of them with carpet tiles on a hard floor, most of them with high ceilings, most of them with acoustic tiles on the ceilings. To grab two examples from the 10, one, as we have here, multi-teacher classroom and one single teacher classroom, which we'll show you in a minute, is interesting to realize that the level of noise exceeded 10% of the time, a level characteristic of how poor the background noise is inside when there are lots of students in there talking, is very little different between the large and the small classroom. The reverberation time, RT, for both classrooms is well within the tolerance or design levels, but the initial surprise for us was the larger classroom, the previous one, with 48 students and 2 teachers, had the lower reverberation time. We decided it was likely from our calculations to be the carpet with underlay and some carpet on the floors. Sarah undertook an ingenious process of asking the students themselves to assess the acoustics of their classrooms. She had them mark up plans for where it was noisy or quiet and where it was hard to hear the teacher's instructions. At first glance, with the multi-teacher classroom, these plans are not to scale above, and the smaller classroom below, there's a clear win for the cellular single teacher classroom. But if we take the other classroom in the same school where that multi-teacher classroom was, then actually there is no clear winner. But rather than rules of thumb around reverberation times and sound levels, what we found was the most important issue here was established through classroom observation. Sarah couldn't quite believe that this was happening at the same time in the same classroom. If I go back to my beginnings as a researcher in building science, I was involved in a survey with George Baird looking at energy use patterns in commercial buildings in Wellington, surveying 1,000 buildings in the CBD. We reported this first in a 1981 Architecture Science Conference, I believe. We measured that model on the right-hand side because LiDAR and other data wasn't available. We obtained dimensions of the building, the volume, the floor area, the percentage of glazing, the nature of the opaque skin. Much easier at the time than walking around the streets doing the same thing. We also obtained every single oil, gas, and electricity bill for every single premise in the city. What we found, to our initial surprise, was that the physical parameters were less important than what people were doing in the building. Many years later, with the assistance of brands, we studied commercial buildings in post-earthquake Christchurch. Tavis Cresswell-Wells modeled the wind pressures that drive ventilation and a range of different proportions of building form, mostly focused on whether it was necessary or beneficial to actually have laneways. These purple surfaces are modeling the next building, shading the building that we were studying. The goal of the laneways was to let in light and air to the sides of the building as well as to the front and back, given that these are buildings that fill the whole of a Christchurch city block the block being 100 meters in the direction that we're looking at and 200 meters in the other direction. What we were interested in, what were the proportions or sizes of those laneways that would work? The exercise established the size of laneways that would help improve energy performance by improving the ability to get light and fresh air through openable windows into the buildings, and the scale of laneway that was necessary. If you followed the European courtyard model, then in fact you could have much better energy performance at the cost of a considerable amount of net lettable floor area, and you could get very substantially improved energy performance, not just in energy use per square meter, but also in total energy. However, the most important part of this study was not the energy use. It was looking at what's like to be in the buildings. We demonstrated that there were real opportunities, even with a relatively narrow laneway, to get very good distribution of daylight across the floor plate. This can be seen in these percentages of daylight autonomy, the percentage of the floor that is lit to our target level of 400 lux across 75% of the space. It can also be seen that those two designs were doing it, one a narrow plan, one a deep plan, with different scales of laneway. And on the right, we can see that from a temperature point of view, there were also designs that worked really well without any HVAC system at all to give us temperatures for nearly 70% of the time that didn't require heating or cooling. That is, those green portions of the bar. All you needed to do from a cooling point of view to achieve this was to open the windows. Took a different approach. He looked at all commercial buildings in the country. He identified a range of different potential energy conservations that could be applied, the strategies on the left. He also looked across a range of different sizes and types of building. Unlike standard models of this type using so-called prototypical buildings, he calibrated his models against the measured data from real data for real buildings collected by the Building Research Association for the B study. Each of these measures, these strategies, was found to have a small effect, such as the effect of advanced daylight measures not changing the window sizes. We get a very slight change in energy performance. But if we applied all of those strategies, then we get a significant reduction effect. Even better, if we only apply this to 1,200 of the nearly 30,000 office and retail buildings in the country, we get 50% of the energy savings potential just with that small change, admittedly across all 1,200 of those buildings. If we go back to our 1981 paper referenced earlier, when you run computer models of buildings, the performance is not normally as variable from one building to the next as we observed in reality, because you're not modeling how people actually use the buildings. The most important parameter we're not modeling or recognizing is that different users manage the use of buildings in very different ways. I would add as a footnote another irony. In that 1981 ANZASCA paper, we also lamented the inadequacy of performance criteria and indices. I believe that 30 years later, that lament remains valid. Back in 1990, I was keen to promote the then fashionable concepts of passive solar. In 1990, I wrote with the help of another graduate student a passive solar design and passive solar construction guide. His name was Ian van der Werf. Much of that early work in the field focused on trom walls and some artificial differentiation between so-called active and passive solar. The focus was on how much energy might be saved. All of the usual: sun comes in from the north, low angle sunshine, under, overhangs and so forth, large amounts of insulation, mass spread evenly and insulated around the outside were covered. focus was on how much energy might be saved. Subsequent books in 2001 and 2010 have tried to remove the jargon to make passive solar design more accessible. Instead of prototypical buildings, the focus was on the role of glass, mass, and insulation in two identified actual buildings. In between the 2001 and 2010 versions of this passive solar design guide, we also wrote a guide to good practice with the Standards Association. We did have some argy-bargy with the people who are trying to defend the role of mass in the thermal performance of buildings. Eventually, we only wrote this about lightweight timber buildings, not concrete ones. However, I suggest we should revisit this approach and should consider the philosophy of listing a guide with better and best practice building design features again today. They could, as happened prior to the 2009 change in the thermal performance specification, signal the next step change in the building code insulation minimum, or could point to daylight design best practice. Meanwhile, market leaders could also use this prescriptive standard to specify levels of design for builders and clients. However, the key problem with all these analyses was we were still assuming when we were modeling that we knew what people wanted or needed in their houses. We have an indication of the current New Zealand Code compliance rule of thumb approach in these two simple heat loss pie charts, comparing on the left the heat losses for a building with the as specified building code R values following industry standard guidelines as to how much timber structure in a wall might compromise its thermal performance. You have an insulated wall with timber, then the timber portion of the wall leaks more heat. On the right, we have heat losses where we've accounted for the extra heat losses due to the larger amount of timber that you find in the walls of real buildings. In our study of thermal bridges for brands, we found allowing for this extra timber changed from 14 to 17% the proportion of total heat loss that was through the walls. This, however, led only to an extra 3% total heat loss. Just as an aside, this slide and the one that follows shows how those heat loss rules of thumb can be used to give important information. The first is extracted from a second-year lecture on one of the many myths that surround passive solar design. It's quoted less often in recent years, but most heat goes out through the ceiling is one that states something that is in fact a total myth. If you put in R values for the roof, the wall, the floor, and the windows for a building that's 20 by 10 on plan with 3-meter high walls and the maximum before you have to do specific design of 30% glass as the windows, and you work out the heat loss by dividing the R value into the area, then you discover that the heat loss that is greatest is actually from the windows, not from the roof. And if you look at a 2-story building, this becomes even more extreme. The heat loss through the roof is 4%. To return to our thermal bridging study, this graph shows the reality we found when we went beyond simplistic rules of thumb. We took real data on the dimensions of the buildings that we had been studying and reported R values for those buildings, plus the measured proportions of timber in the walls. We've pictured here the likely heat gains, which are those parts of the bar that are above 0, and the heat losses. The brown areas, these areas here, represent the amount of heating energy that we actually need to buy. The red-orange color is the amount of solar gain in through the windows. We've accounted for the heat gain from people and lights in the building, assuming certain standard uses of the building. The first two parts of the bar below the 0 line represent the heat loss due to the air leakage into the building and due to openable windows. Note, because the windows are large, even in the middle of July, we're opening them to get rid of the solar heat gain in through these large windows that are facing north. Now, the square box represents the heat loss through the windows and through the rest of the fabric of the building, the roof, walls, and floor. I've added to the complexity of this graph by representing the as specified and as built. So roughly 20% of the wall is timber, roughly 30 to 35% of the wall is timber in the as built example. So we have for each month, January, for example, 2 bars. The one on the left is the as specified, the one on the right is the as built. The really strange thing for us was here and here. The total energy use for the building with better thermal performance in the walls, less timber leaking heat in the walls, was for the as specified compared to the as built building, heating and cooling. And you can see that if you look at the circled area here, the total for the windows is the same because the windows are the same in both cases. It's just the heat loss through the roof, walls, and floor, and in fact just for the walls, that is increased, and the physics is being represented properly. That is, the heat loss through the opaque fabric is correct. But we seem to be defying the laws of physics with the result. What we learn from this is what's making the difference is how much we're assuming people are opening the windows. That is, we open the windows when it gets too hot. It gets too hot less in the building that has the greater amount of heat loss, the greater amount of timber in the walls. It's all about how we were modeling the behavior of people in the building. So what I've learned from this and the other studies is that detailed performance pictures of lighting, acoustics, and energy are far more important than simplistic daylight factor, reverberation time, or heat loss calculations. Even the improved monthly heat balance calculators such as PHPP or ALF, which allow for solar gains as well as heat losses and thermal bridges, do not help look at anything other than energy. Simplistic rules of thumb calculations make design decisions made early in the design process easier. They can be made more quickly. However, it is clear that those early design decisions, which are recognized to commit the building and its users to a high or low potential performance, are unlikely to represent the true livability of the building in reality. They don't tell us what it's like to live in the building, nor will they tell us anything that is useful to help us with the purchase of a building we'd like to live in. They clearly will never predict my personal energy use. Even if you measure the actual performance and use, if you measure the temperatures in buildings or the energy use, for example, you get no information about livability unless you measure 1, the temperature that was delivered as a result of 2, the energy used, and 3, unless you talk to the people as well about how they're using the building, then you have no way of knowing how well the building itself is actually performing. We must look at what people really want inside buildings. It's not some arbitrary 18 degrees Celsius value, such as often quoted as sourced from the World Health Organization. It's much richer and more complex issue than that. It would be remiss of me at this point not to highlight the dilemma documented by Lauren Christie talking to consumers way back in the early 2000s about their house purchase decisions. Another PhD student, she identified a serious issue about the disconnect between homeowners' desire to act sustainably and their actions. Homeowners understood the value to them of the energy efficiency or low carbon options they had, but they would not choose them unless everyone else did so. To this market perversity, I would add Germán Molina's current research, where it is becoming clear house buyers are looking for very different comfort performance than designers typically intend. They also don't trust vendors or vendors' agents to tell them anything useful about how a building might perform. On the topic of PhD students, I'd like to conclude by referencing the shoulders I've stood on that have enabled this think piece. This list is indicative of the framework of research I'm currently involved in and are the reason for the People and Buildings title. What I realized in putting this together is the students that I'm currently supervising for PhD are mostly focusing on different aspects of this livability issue. They're talking to people, understanding the important things about how we use and design our buildings and the environments that those buildings create.